Okay, so welcome everybody. This is the Rubin Research Bytes, Session G, Survey Strategy and Solar System Science. Your chairs are Lynne Jones and Phil Marshall. And the plan is I go through this welcome and introduction, reminders of the code of conduct and so on. And then we will have 4 flash talks, 3 minutes each. And these talks are about SNAPS, the Solar System Notification Alert Processing System by David Trilling, Chasing the Loudest Gravitational Wave Sources, the LSST Perspective by Andjelka Kovacevic. I'm sorry, practiced that and I just, anyway. Optimizing the LSST Wide Fast Deep for Dark Energy Science by Humna Awan, and Unknowns in the Rubin Observatory LSST Era by Fabio Ragosta. And at the end, we will have our question and answer session. We have about 10 minutes reserved at the end for that. So, let me please remind you, you've seen this in all the other sessions as well. We do have a code of conduct for this workshop. And this is important for us and important to follow. And also, a reminder that this session will be recorded. If you don't want to be recorded, you are welcome to leave your camera off. You can ask questions through the Slack channel or the Zoom chat. At the end, when we get to the question and answer period, if your question, if you'd like to ask a follow-up question or so on, you can ask to be unmuted and we can do a limited number of questions that way. The videos will be posted tomorrow. You can use the reactions in Slack. Oh, I guess it's in Slack, yes. When you see questions on the Slack channel, so there is a Slack channel for this session, you can give a thumbs up if you want more emphasis on a particular question, if that's a question that you share interest in. And you can also applaud using the little applaud emoji. You can access this presentation material from the session page as well. All right, so with that, we will start with our first presentation, SNAPS, from David Trilling. Let me unmute you. Or oops.
Test, test, test. Okay, cool. Thanks, Lynn. Thanks, everybody. I see all your names and some faces. I'm David Trilling. I'm going to talk briefly today about SNAPS, the Solar System Notification Alert Processing System. The overview is that this is a broker to ingest solar system object observations and do stuff with them. Well, I guess you can't see my mouse because it's Lynn's mouse. I'll just tell you that on the right side is a kind of a flow chart, architecture diagram, and the key points are also here on the left. So starting at the top of this flow chart, we're going to ingest alerts from ZTF or maybe Atlas or maybe LSST. In some cases, we ingest, we have a pass-through from Antares, so we're ingesting a substream from Antares. We have a database, we're ingesting on the left side, it says MPC and others, so data from additional sources. The path on the right with the red is a real-time outlier detection scheme, and on the left is a blue, that's the daytime detection scheme, and I'll show you examples in a moment. And we have a database that is will be published, and we will issue alerts both in the nighttime and the daytime outlier detections. Next slide, please. Thank you. On the left, these are histograms. So we're currently ingesting data from ZTF. And so on the top and the bottom on the left are the same data, just scaled differently. This is number of observations for asteroids. So we have, 1,500 asteroids with 40 observations or more, and some asteroids with 100 observations or more, and so on. On the right side is just an example, one of those asteroids, 4 panels here, and the top is just the data record. The second panel is a lone Scargill periodogram. Third panel is the phase data, and the fourth panel is residuals, just to give you an example of what we're doing automatically for every asteroid. Can you go to the next one, please, Lynn? So schematically on the left, if an object has a nighttime or a real-time funny thing happening, and that's shown, we have this sine curve here and two blue points that are unexpectedly bright, we would issue an alert. On the right side, we have daytime or population outliers. We have all these black points, and then these two blue ones are outliers, and we would issue an alert on those as well. And the last slide, please. Just to show you on the right side, these are real data from ZTF. And again, we have two features here. This is color and light curve amplitude. And these are standard deviations. And again, we look for outliers in this space. Thank you very much.
Perfect timing. Thank you, David. Next, we have Andjelka Kovacevic.
Thank you. Until space-borne gravitational wave observatory LISA is ready to fly, the question is, can we catch photons of compact supermassive binary black holes with LSST? We know LIGO double black hole mergers are totally photon-free, but here, theoretically, yes, we can catch photons because bond accretion rate scales as mass square of the object. Second, emerging galaxies' dynamical disturbances are pushing gas to the center, and binary remains as bright as a quasar almost up to the merger. Also, binary accretion rate is modulated periodically and may be rendered into periodic signal in the light curves. Technologically, yes, we can catch photons because LSST instrument is fast enough to monitor binary in real time, even during the final stages of merger. Next, please. Next, please, slide. But Mayday call is in methodology comprising Shakespearean dilemma to roll or not to roll the cadence. Rolling cadence will prohibit combination of LSST photons and LISA gravitons into multi-messenger information. But cadences of few days because of filters alternation would produce sparse LSST light curves. In such situation, we can craft LSST periodicity search flow with incorporated novel machine learning based methods. Such tool is our 2D hybrid method on the left, comprising Gaussian process learning of light curves. Our method correlates matrices of continuous wavelet transforms of Gaussian modeled light curves. We end up with the map of correlated periodic signal present in both curves. Contrary to periodograms, our method doesn't a priori assume the form of an underlying periodic signal. On the right, you see envisioned LSST periodicity search flow combining two blocks, classical and novel methods with our method init. Then classification of object as binary candidate can be done via statistical decision. Next slide, please. Finally, we predict cadences required to determine periodicity with 13% accuracy based on our method applied on decennial long-term light curves of active galactic nuclei. We base our metric on object variability, the ratio of cadence, and the period of underlying signal and redshift. In table, we see at redshift 7 for 20% variable object, the cadence would be 12 days. But for 10% variability, cadence is 5 to 6 days at redshift 4. The central the figures show that the expected error across redshifts will be smaller for more variable objects. Going back to our question, yes, we can chase photons of compact supermassive binaries, but without rolling cadence and crafting carefully periodicity search flow with viable methods. Thank you.
Hi everyone, my name is Humna Awan. I just finished my PhD at Rutgers University and working with Eric Goizer, and I'll be starting a postdoc at the University of Michigan later this fall. I will be talking about some of the work that we've been doing in the DUSK, Dark Energy Science Collaboration, to optimize the LSST Wide Fast Deep survey for dark energy science. Next, please. So sort of lay out some of the details, the LSST science requirements document mentions some specifications for this main survey. Specifically, we have about 90% of the LSST time that will be spent on this main survey, yielding about 18,000 square degrees over 10 years. The SRD also mentions the median number of visits to each field and also the single visit depth for these 6 bands. So using these specifications alongside other cadence parameters, you can basically simulate what the survey would look like, and that sort of yields the current baseline, for instance. Next, please. So here's a sky map Oh, there you go. So that shows like the baseline. In blue is the main survey footprint, and in pink is the basically non-WFD regions. Overlaid here is also the DESI footprint. One thing I want to highlight, the main survey footprint. So the blue swath does not include the galactic center, but it does include the galactic anti-center. Okay, next please. So aside from the LSST science requirements, we have specific needs for dark energy science. This includes having good photo Zs, deep galaxy samples, low dust uncertainties, and as large area as possible. Next, please. So now with the dark energy science needs and the current baseline, what ends up happening is that we lose about 25% of the LSST survey footprint and effectively LSST survey time, primarily because of high Milky Way dust accumulation regions. And that's a huge loss. Next, please. So in order to circumvent this problem, what we have proposed is to basically reconfigure how LSST time is spent. Specifically, what we are pushing for is like spending about 70% of the planned LSST WFD time at low extinction regions and extending the footprint north and south in order to yield the 18,000 square degrees that we can actually use for extragalactic science, and basically leaving the remaining WFD time for galactic science itself. So here is the sky map. The yellow is basically the proposed footprint, and you can see it avoids the galactic plane and increases overlap with spectroscopic surveys. Next slide, please. So just to sort of summarize, we sort of accept that effectively nearly 70% of the WFD time will be used for extragalactic science. What we are pushing for is basically reconfiguring how that time is spent to get as much area as possible. So if you have any ideas, thoughts, please reach out and also join the conversation tomorrow and during the survey strategy session at 10:30 PT. Thank you.
Thank you, Humna. And last we have Fabio.
Yes. Hi. This is a project that was in a collaboration, running in a collaboration with Shalom Link, Federica Bianco, and with Clarkson, and it was focused on the scouting of the best observational strategy for discovering new phenomena with LSST. Next, please. The simulation were run into metric analysis framework, which is a framework that allows us to use a set of tools to analyze data set from the OPSIM simulated survey to help understand the effect of telescope scheduling and on survey performance. Next, please. We focused on what we call true novelties because as is shown in the parameter space figure from Kovacevic et al. 2019, there is an empty region in which there were no discoveries at all of new kind of phenomena. So we analyzed the feature space characterized by the brightness, color, time evolution, motion, morphology, and association, as is represented on the left of the slide. The bolded features are the ones that was included in our metrics. The other two we're still working on, and we analyze the ability of the surveys of the different observation strategy through the four metrics that was shown at the bottom of the slide: likelihood score, confusion index, proper motion transient, and time gaps. Time gaps metric was developed by Shalom Link. The first three analyzed the proper motion, the true novelties area of our investigation on the part of the figure of merit. Next, please. We analyzed the fraction of the real true novelties we can detect with LSST. Next, please. And the quality of the detection into modeling a structure going deeper in the universe or in a denser environment. Next, please. Then we aggregate all the results in the bar plot that allow us to ranking all the observation strategies. Next, please. And here I show the time gaps distribution between the two observations in the same filter on different filter related to the decay divergency parameters to analyze how is the distribution discrepancy of the distribution to the ideal uniform distribution. Next, please. And this is the results of the last analysis of the time gap distribution for all the databases as we can show until now. Thank you.
And thank you to all of our speakers. Now we have some time for some quick questions. Phil has been monitoring the Slack channel and the chat channel in the Zoom meeting. So hopefully Phil can fill us in on what we should, on some questions.
Yeah, absolutely. So I see 3 questions so far. We have plenty of time actually. While we've been listening to our 4 talks, the other Zoom rooms have been having connection issues. So I think we have an extra 15 minutes to hang out here, because the handover time will now be 11:15 instead of 11. So plenty of time for questions. So keep writing them into either the Zoom box, chat box, or in the Slack channel, and we can start going through them. So let's wind back to David's talk. Tim Lister, are you out there? Would you like to unmute and ask David your question?
Can you hear me?
Yeah.
Okay. So a question for David was, what sort of size database or number of objects have you tested snaps with for determining the periodograms?
Thanks, Tim. I have 2 answers for you. One is mentioned here, actually, the slide we're looking at. The 5th bullet on the left side mentions that we have a synthetic population. So in addition to ingesting ZTF, we also have built a synthetic population and run it through all of our schemes. And then, of course, we can test the derived period to the inserted period. And I think we're running that on 10,000 objects, but we do it over and over again. And so not only can I tell you, well, that gives us a sense how good our solution finding is. With ZTF, we have, I don't know if this is totally up to date, but it's pretty close, 4.5 million observations of not quite 300,000 unique asteroids. And probably that's it for ZTF. We're not going to get a lot more new unique asteroids because we've been around the sky once. And so everybody who's brighter than the detection limit we've already got, and everybody else we're probably not going to get.
Great, thank you. Because we have so much time for questions, I think everyone will get plenty of airtime. So I'm going to stay with David for just a minute. Gareth Francis, you were out there. You had a question for David.
Hi, David. So your 2 arrows going off the bottom there, where you're republishing unusual alerts. What technologies are you anticipating scientists using to receive those? So how are you expecting people to interact with you?
Yeah, so ignoring the database, but the alerts, we're going to have a Kafka stream. That is our plan. It's not built yet, so if somebody felt really strongly that we should do something else, I would listen to that. But the idea is to be as nearly similar to the alert streams that are coming from the surveys as possible.
Great, thank you. And then we have a 3rd question for David. Wes Fraser, are you out there?
Sure am. Hi, David. Great that you're working on this. Just really curious how you're determining an object's sort of live color and phase information. That sounds like a very challenging thing to do given the sporadic filter changing nature of the surveys that you're talking about.
Lynn, I'm sorry, could you go to the next slide? That might help just show this. Thanks, Wes. Nice to hear from you. Nice to hear from all you people out
hey,
there.
Canada's here.
So in the top panel here on the right side with the red and green dots, is showing the green and red is the G and R band observations from ZTF. So this one actually was not so terrible. You know, we can find the periodogram, and then we have an iterative technique to determine the phase function. We fit each of the G and R bands separately in terms of deriving the mean absolute magnitude, but we combine those data in terms of deriving the period with an arbitrary offset. And so if you do that iteratively, you can get a period solution and a color solution.
And then you sort of extrapolate that to the observation in question to see if the color has changed?
Yes. So I don't have that plot here, but we then do a sort of a season by season. At the moment, we're doing season by season comparison of color changes.
Okay, thanks.
You can't really derive an instantaneous color because you only get one band at a time, right? So
yeah, exactly.
G, and then you have to guess what the R band is. So extrapolate the light curve, and then we say, okay, well, we think we know what the R band should have been at that time, and we know what the G band was at that time. And so then we can derive in quotes instantaneous color. That's only as good as it's going to be in terms of the survey. But of course, if you got 3 colors in a row, that seemed kind of weird, then you would have more, you would believe it more.
Thanks.
Excellent, thank you. I see there are even more questions for David, but let's take them to Slack so that we can give the other speakers a chance to get grilled. Carlos Gonzalez-Fernandez, are you out there? You have a question for Humna, I think.
Hi, yes.
Carlos, it was really hard to hear you. You're incredibly distorted. Would you mind if I just read your question off from Slack? Is that okay? Perhaps better even, don't even answer that. I don't know why it's just so distorted. Anyway, Carlos's question, Humna, was, would you gain anything by adding wideband near-infrared data on your survey area, either helping with Milky Way extinction or adding data for photo-Zs?
So I'll answer the second half. Photo-Zs, of course, benefit from more band data, so that definitely will help. Having coverage for the same footprint in a different band beyond the LSST 6 bands. For Milky Way dust extinction, the limiting factor is Milky Way dust uncertainties, and my understanding is that I'm not an extinction expert, but the experts have quoted like an extinction limit that basically beyond that extinction, the uncertainties are too dominant. So I'm not exactly sure whether it would help. I can inquire, of course, like Eli Rykov has been the main person sort of pushing for this extinction cut. Yeah, sorry.
Yeah, I hope that addresses your question, Carlos. I guess maybe the idea here could be if you were able to combine data from some other survey like Euclid or so on, maybe you could live with a smaller, cutout area or something like that, and make it even more efficient than the plan you have.
I had a very small clarifying question. When you say 70% of planned wide fast deep time, that's 70% of the 90% that you mentioned at the start. Okay.
Yes.
Just to be clear, in general, we are unlikely to spend 90% of the time on wide fast deep itself, but in a way, because of how you're defining what the wide fast deep here is, I think they're completely compatible.
So the SRD mentions 90%. Do we have a new number for what the number would be for WFD?
Sorry for the dog in the background. So there is no requirement to spend 90% of the time on wide fast deep. What it says in the SRD is we expect to spend up to 90% on wide fast deep. It turns out that you can cover 18,000 square degrees with 825 visits, which are the SRD requirements, with a much smaller fraction of the total time. But that is completely compatible because if then you're saying actually 18,000 square degrees of low extinction time, and then put some of that time into the plane, which is essentially what I'm taking away from this, then it's equivalent, right?
Great, thank you. Thank you for the clarification, and also for the sound of the pet in the background, keeping everything cheerful. Let's move on. So Kanya Chakrabarti, are you there? You had a question for Fabio, I think.
Yeah, hi, thanks. I just wanted to ask, what are you assuming for the accuracy of the proper motions and the detections of the true novelties?
Yeah, so we measure the proper motion and at the level of milliarc second per year. We measured the motion of, we simulated the motion of object that move at least the 5% of the full width and maximum of the PSF, of its PSF. So the measurement are run on just a simulation of actual sources that move in at least of a 5% over the 10-year survey of the LSST. I hope it answered your question. Otherwise,
yep. Okay, thank you.
All right, great, thanks all. Let's see, there we do have more time for questions. While you think of those and typing them in, just a bit more on the transition to the next session. We've had to find replacement Zoom rooms for the other sessions. Session G is working perfectly, as you can see, but the other sessions, some of them have new Zoom rooms. So the thing to do is to go back to the general channel on Slack and see which Zoom rooms have been have had to move. So the general channel has the information, and I'll put a link there in our channel and in the Zoom chat as well. Let's see. I see somebody's typing. So go ahead and we'll see what question you have. I think this is Rob Seaman. You're out there. You have a question for David about snaps.
Yeah, just can you hear me?
Yeah.
Yeah. So if you have a discordant point in a moving object, it can be because the moving object is an active asteroid or something, but it could also be because there's a mislinkage. How will you resolve that issue?
Yeah, so the ZTF alert stream is only sending us asteroids that are known identified asteroids. So in the alert, it says, this is asteroid whatever, and then here's our new photometric measurement. So we're not doing any linking. Linking is done upstream from us, and so I'm frankly just not paying attention to it. You could imagine on this plot we happen to be looking at here on the right that if you had an outlying point that somehow snuck through the linkage but was clearly wrong, then we would have very low fidelity solutions, and they would get flagged, and we just kind of ignore them because eventually they would get cleaned up. So we're not handling that very real concern you said. Is just not we're not dealing with it.
Okay, I think what you just said is it may cause a single discordant point, but it won't continue to affect the curve.
That's right. And also since the linking is somebody else's problem, I'm just going to let them continue to solve it, and I'm not dealing with it.
Yeah, we'll see how that works.
So I actually am not concerned about like mislinking in detection so much. I mean, you're right. Like it may happen. It happens at the MPC after all. What I've seen in the ZTF stuff for comets, for example, is that you get background sources coming into the aperture, and it happens. It's going to happen for stationary sources at some point, sometimes too, when we get asteroids overlapping the stationary source, and it's just something that probably needs to be accounted for when you're consuming an alert stream.
Yeah, Yeah, that's right. I mean, we also, so I'm not showing, but we also have postage stamps for all of these sources, which we don't really want to look at, but you could. But sure, you know, if you study this data we're looking at here, you could put your fingers on one and say, oh, that looks like some kind of strange outlier point, and it could be just photometric noise, or it could be that you drove over a galaxy and it our photometry is suspect in that case. So, you know, one of the things we're going to do in the alerts that we broadcast is give a score, like a how much do you believe it kind of score. And there's various parameters that go into that, and we will continue to tune them as we have more experience dealing with it. So if you had just one outlying point, that would be really interesting if it was real, but we're not sure if it's real, that get some kind of score. Whereas if you had 3 or 4 or 5 outlying points in a row that all had a score that you believe, then you could start to act on it if you have a follow-up telescope. If you have a follow-up telescope with lots of time available, you can follow up anything you want, and you can rank them by score, most believable to least believable.
Yeah, and getting the phase curve wrong will also make effects like this as well, that actually will kind of increase over time as well.
Yep. But that is also self-correcting. We have some experience with that. Yeah.
Okay, thanks.
All right, thank you.
Thanks,
So
Lynne.
if you don't have another question, I'll leave. Okay.
Actually, I was going to play my co-chair card. I had a question for you and Andjelka. You mentioned that rolling cadence wasn't good for your application, which is interesting, right? Because there was a lot of hope around rolling cadence being the solution of all problems. So I'm wondering if you could say a little bit more about why rolling cadence is bad and what you would like to see instead.
Thank you, Phil, for this question. Yes, that is really, how to say, Hamletian question, to roll or not to roll. Why not to roll for the detection of the oscillations? Because during the half of the year or 1 year, you will just monitor one part of the sky. And then you're going to other. And with this, we will lose actually the points in the light curves. So our light curves will be, you know, without information, and we will have, in this part of the year without observations, we will not have information in the light curve. But for the tracking of the periodicity, it's really good to have good coverage of the data points over the observational timeline base. And for example, with these smaller cadences, about several days, we can actually achieve, for example, several dozens of points per year in each band. It is not, how to say, so dense coverage, but we can use machine learning methods to learn actually the curves. And we applied our method on several cases, even the famous PG 1302-102, to show actually periodicity in it, even that new data analyzed by Lynne et al. By Lee et al. In 2018 suggested that there is no periodicity after adding new information, after adding new data. And what we actually discovered in this object, that we modeled also the object with the model in which we have some type of temperature declination, like type of the cold spot. Because of this, we can see actually the deterioration of the periodicity signal in the light curve. So actually, as much as we can get the points in the light curves, we can actually follow the information. We know that, that maybe these cadences which are rolling maybe are better for some other static sciences in astronomy, which doesn't require actually updating the information during the long time of period. So actually, rolling cadence wouldn't give us information in certain period in the light curve. We have the light curve as you have in the asteroids observations. And for example, you are missing in 1 year or one period data points. It is interesting that our method can be applied on also asteroid light curves as well, because our method is not only connected to the AGN objects.
That's great. So we have a couple of follow-ups to this question about the long gaps with missing data. Maybe Humna could ask hers first, and then Michelle after that.
Thank you.
Yeah. So I'd be curious to know, like, rolling cadence, like what is like the period or like the cadence that you're looking for? Are you thinking about like 2 deck bands or 3 deck bands, or how frequently do you go back? Like for static science, for instance, we are interested in like good uniformity, large area, like for like data releases, for instance, like year 1, 3, 6, 10. So if something happens in between those years, our science isn't impacted as much. But then, for instance, if you only cover half the sky for the first 3 years, the dark energy science will suffer a lot, right? Because the area is such a critical thing. So is there like, is the science going to benefit from a specific kind of cadence, like rolling cadence, or is it just any rolling cadence? Sorry if I missed this already.
Let me try to reveal the question more. You are asking me about the cadences which we are requiring.
Right.
In our
yeah, so when you say that rolling cadence will be good, what kind of rolling cadence? Are you thinking divide the sky in 3 declination bands and basically cover the first?
Yes, I'm sorry. I am saying that rolling cadence would be okay for some other types of investigations, but it is not okay for our, because the information, the light curves from the supermassive binary black holes are coming from the innermost stable circular orbit, which is very, very close to the supermassive binary black hole. And that is actually information coming from the environment, which is non-linearly coupled with the supermassive binaries. And because of this, it is really difficult to catch the signal, because supermassive binary warps the space-time around it. So because of this, we need, because of this specificity of general relativity, we need such really fine or fine cadences in order to sample the information during the observational period. But rolling cadences are good for some other sciences in astronomy, but not for the time domain following the periodicity and detected candidates for gravitational wave observations. Because the information is coming from the very, very heart of the gravitational potential, which is actually perturbed by the supermassive binaries. That is really, really tricky, and it requires fine tuning and nice cadences. Our method has been working on cadences about 80 days, even on the period of observations of 20 years. So perhaps even such cadence can be enough to catch the information.
Yeah, certainly sounds like what Michelle is about to say might be of interest. Michelle, do you want to just follow up to that real quick?
Yeah, so the recent simulations that Lynne and Peter have been working on, all of the rolling cadence simulations include some fraction of time which covers the remainder of the sky, and they have various different options, 10%, 20%, 30%. So the idea being that even if you roll for half the sky for half the year or whatever the strategy is, the sky doesn't remain unobserved for such a long period of time, but the cadence in that region obviously would drop quite a bit. So what you would end up with is you would have these, your longer periods would effectively be more sparsely sampled, but you would never completely lose samples. And then you would have periods of time where you would have very, very good cadence, which is where your rolling cadence would be. So it might be of interest to have a look at some of the more recent proposed rolling cadences. It might not be as bad as you think.
So what do you propose? To combine something between the rolling cadences and these finer cadences? Am I?
So all of the new, I mean, Lynne can probably comment on this, but all of the more recent rolling cadence simulations, you never switch off a region of sky completely.
Okay.
So you'll never go for 6 months without observing a particular field, for instance. So,
Yes, because it's so devastating, actually. And if we can achieve some kind of agreement, you know, that we can populate with information and not to lose it. For example, in the case of the PG 1302 object, we had actually very dense observations by assassin telescope. And in that dense section, there were actually information that something happened in this object, very strange. And it seems like the temperature dropped in that period in the accretion disk of the supermassive binary black hole due to some reason. So actually, as much as we can get dense points, that will be great. There is also great possibility to lose information and also to come to some conclusions which are not consistent with the real state of the nature of the object. That can be tricky, I agree. Perhaps this is the, how to say, the decision, how much we will lose and how much we will, you know, to have in our hands. But we witnessed it that assassin dense data points revealed really, really interesting information. If this part of the light curve were covered by lower denser points, we will completely miss what happened in that time in the object.
Yeah, it's all about understanding the trade-offs, isn't it?
So I agree. There have to be some kind of balance between the decisions.
Absolutely. All right, I think we might have reached the end of our list of questions. If you do have more questions, please do type them into the Slack channel for this session G. The speakers are there and they're paying attention, and a good chance to interact with them after this session. Lynne, I think it's pretty much time to transition.
I was just going to say it is time to let everybody go so they can find their new Zoom rooms. Please note, as Phil pasted into the chat, the Zoom rooms have changed, so go back and look at the general session to find where you should be going next. Thanks, everyone.
Thank you.
Thanks very much for the talk, speakers. Thank you.
Thank you.
Thank you to the co-chairs for hosting.
Too kind, Tim. All right, don't go anywhere, speakers. We've got more audience coming for you.
All right, go and.
Yeah, what I haven't been doing, Lynne, is looking at the participant list to see some people leave and other people arrive. But
yeah.
I trust that will happen at 11:15 around right about now. So I'll watch their names now as you fiddle with the slide deck.
Yes, I need to go and. Oh, Safari. Not what I usually use. Okay. Do you happen to know which slide it was that Fed changed? Oh.
I think it was one of it was one with a science collaboration logo on. So you literally just have, I think you just have to present again and it will be fine. There's no editing to do. Okay, so it looks like we do have a bunch of new people in the audience. Hello there, everybody. At least all the people that asked questions in the previous half hour have gone somewhere else. So we've got fresh questions coming your way, speakers. While Lynne puts the slides back up, hopefully everyone is paying attention to either the Slack channel for session G or the Zoom chat. That's where you're going to be asking your questions as they spring to your minds as you listen to the talks. All right, mute myself again.
And we are back again. Are people still coming in, or we do have lots of new people? All right. All right then. Welcome everybody to the second session of the Rubin Research Bytes. This is session G for Survey Strategy and Solar System Science. In this session, we have 4 talks. So first, I'll go through a quick introduction and reminder of the conference rules, and then we'll go through 4 talks on SNAPS, the Solar System Notification Alert Processing System by David Trilling, Chasing the Loudest Gravitational Wave Sources, the LSST Perspective by Andjelka Kovacevic, Optimizing the LSST Wide-Fast Deep for Dark Energy Science by Humna Awan, and Unknowns in the Rubin Observatory LSST Era by Fabio Ragosta. And at the end, please save your questions, well, write your questions in the chat as we go along. At the end, we'll go through and either Phil will write your question or reword your question, or invite you to unmute to present your question. All right, so as a reminder, we have a code of conduct for this meeting, and you are all, at this point, I expect you are all familiar with this code of conduct, and you've read the code of conduct on the website, and just please be aware we're following that code of conduct. And also, this talk is going to be recorded. If you don't want to be recorded, you are welcome to keep your camera off. The videos will be posted tomorrow on with a link from the session agenda. You can ask questions in the Slack channel, which is great, because then you can give thumbs up to other questions that you would also like to hear the answer for. Or you can paste them into the chat channel for the Zoom meeting. And you can show your appreciation with the little clap emoji at any time. The slides are also available linked from the agenda webpage. So with that, let's start with our first Research Bytes talk from David Trilling.
Thank you, Lynn. Thanks everyone for strolling in. I'm David Trilling. I'm going to talk about SNAPS, the Solar System Notification Alert Processing System. This is a broker that will ingest solar system object observations. We are currently working on the ZTF alert stream, and we will gear up to get on the LSST alert stream. The architecture is shown here on the right with some key bullets on the left. So just starting at the top on the right here, the alert stream is coming from a sky survey. In some cases it passes through Antares, and we're listening to a substream from Antares. We ingest these observations into a database. There's an arrow coming from the left that says MPC and others, so we're ingesting other databases as well. We have 2 main things that we do. We produce, on the right side, it says real-time or nighttime alerts. That is an outlier or unusual behavior that happens right, and we can detect it right away. And on the left is a daytime processing where we compare an object to all the other objects in its population, and we can detect outliers in that way. Next slide, please. Thank you. So this is some example data from ZTF. We've been listening to the ZTF data stream for, I don't know how long, however long it's been going on. On the left side in the two histograms, these are, it's just showing the data records that we have. So for example, we have, you see in the bottom panel, we have about 1,500 asteroids that have 40 or more observations. On the right side, this is just an example asteroid. 4 panels here. The top panel shows the photometry. Second panel is the Loam-Scargill periodogram to derive the period, rotation period. Third panel is showing the phased data, and the fourth panel is residuals. Next slide, please. Thank you. So as I mentioned, we have two kind of outliers that we're looking at. We have a real-time or in-the-night outlier, and then we have a daytime. So on the left side here, I'm showing an example of a real-time object. It's coming in from the left side with this nice sinusoidal behavior. And then we have two data points that are weird. They're outliers for some reason. And so we can trigger, issue an alert on those. On the right side, this is now a bunch of objects, feature 1 and feature 2, two derived properties. The black dots are all the background population, and we have these two blue dots that say, hey, this is an outlier compared to the population. Last slide, please. Thank you. So on the right side, this is data from ZTF, a small subset of the data, and I have standard deviations of color on the x-axis and light curve amplitude on the y-axis. And again, we're looking for outliers in this feature space. Thank you.
Thank you, David. Next, we have Andjelka Kovacevic.
Thank you. Good evening from the Belgrade. Until spaceborne gravitational wave observatory LISA is ready to fly, the question is, can we catch photons of compact supermassive binary black holes with LSST? We know LIGO double black hole mergers are totally photon-free, but here, theoretically, yes, we can catch photons because bond accretion rate scales as mass square of the object. Second, in merging galaxies, dynamical disturbances are pushing gas to the center and binary remains as bright as a quasar almost up to the merger. Also, binaries accretion rate is modulated periodically and may be rendered into periodic signal in the light curves. Technologically, yes, we can catch photons because LSST class instrument is fast enough to monitor binary in real time, even during the final stages of merger. Next slide, please. Next slide. But Mayday call is in methodology comprising Shakespearean dilemma, to roll or not to roll the cadence. Rolling cadence will prohibit combination of LSST photons and LISA gravitons into multi-messenger information. But cadences of few days because of filters alternation would produce sparse LSST light curves. In such situation, we can craft LSST periodicity search flow with incorporated novel machine learning based methods. Such tool is our 2D hybrid method on the left, comprising Gaussian process learning of light curves. Our method correlates matrices of continuous wavelet transforms of Gaussian modeled light curves. We end up with a map of correlated periodic signals present in both curves, similarly to the two-dimensional spectroscopy. Contrary to periodograms, our method doesn't a priori assume the form of an underlying periodic signal. On the right, you see envisioned LSST periodicity search flow combining two blocks, classical and novel methods. Then classification of object as binary candidate can be done via statistical decision. Next slide, please. Finally, we predict cadences required to determine periodicity with 13% accuracy based on our method applied on decennial long-term light curves of active galactic nuclei. We base our metric on object variability, the ratio of cadence, and the period of underlying signal and redshift. In table, we see at redshift 7, for 20% variable object, the cadence would be 12 days, but for 10% variability, cadence is 5 to 6 days at redshift 4. The figures show that the expected error across redshifts will be smaller for more variable objects. Going back to our question, yes, we can chase photons of compact supermassive binaries, but without rolling cadence and crafting carefully periodicity search flow with viable methods. Thank you.
Thank you. And next we have Humna Awan.
Hi, my name is Humna Awan. I just finished my PhD at Rutgers University with Eric Goizer, and I'll be starting a postdoc at University of Michigan this fall. So today I wanted to describe some of the work that we've been doing in DESK, which is a dark energy science collaboration, in an attempt to optimize the LSST wide fast deep survey for dark energy science. Next, please. So to lay out some of the details, the LSST science requirements document mentions some specifications for the LSST main survey, which is the WFD survey. The idea is to spend about 90% of the LSST time on WFD, yielding 18,000 square degrees over 10 years. The SRD also mentions the median number of visits to each field, and then also the median single visit depth for the 6 bands. Now, using the specifications and other parameters for cadence for observing strategy, we can simulate what the survey would look like, and that basically leads to what we have as the baseline footprint. Next, please. So here's a sky map that is showing what we have right now. In blue is the WFD baseline footprint, and in pink is the non-WFD regions. Overlaid here is the DESI footprint in green. One thing I want to highlight here is that the blue, blue part, which is the WFD baseline, does not include the galactic plane, galactic center explicitly, but it does include the galactic anti-center. Now, aside from the LSST science requirements, we have specific needs for dark energy science. Next, please. And these needs include a good photoseize, deep galaxy samples, low dust uncertainties, and as large area as possible. Next, please. So with these dark energy science needs and the current baseline footprint, what ends up happening is that we lose about 25% of the survey footprint and effectively 25% of the survey area for extragalactic science, mainly due to high Milky Way dust extinction. And this is a huge loss. So in order to circumvent this, we have a proposal that we've been pushing. Next, please. Our proposal basically says to reconfigure how the WFD time is spent. Specifically, what we are saying is to spend about 70% of the planned WFD time at low extinction regions, extending the baseline footprint north and south to basically yield 80,000 square degrees of survey area that we can actually use for extragalactic science. And then basically the proposal says that the remaining WFD time can be spent on galactic science with this specific optimized cadence for its science. So specific implementation of this is shown on in the sky map here. Blue again is the baseline from before. Yellow is the proposed footprint. And as you can see, we are basically cutting out the galactic plane and then also extending north and south, increasing the overlap with the spectroscopic surveys and giving us the 18,000 square degrees that we want. Next, please. So effectively, our proposal is kind of accepting the specific time that will be usable for extragalactic science, which is about 70% of the WFD time. What we are saying is that instead of spending all that time in regions that we end up not using, we would like to kind of maximize the amount of area that we can get with that specific time. If you have any questions, please reach out. Thank you.
Thank you, Humna. And our last talk is by Fabio Ragosta.
Hi, I'm Fabio Ragosta from the University of Naples Federico II. This is a project run in collaboration with Lynne and Federica Bianco and Will Clarkson on the discovering of new phenomena with the LSST. Next, please. All the simulations were run in the metric analysis framework, which allow us to use a set of tools to analyze data set from the OPSIM simulated survey to help understand the effect of telescope scheduling on survey performance. Next, please. The true novelties or unknown are sources that are still not discovered that lie in the empty region of the plot of Ivesic et al. 2019, and we aim to emphasize the ability of some observation strategy to detect those sources through analyzing some features as the brightness, the color, time evolution, motion, morphology, and association with our metrics, light score metrics, confusion index metric, proper motion, time gaps. The last one was developed by Lynne. The first three are analyzing the proper motion area measurement of our analysis. Next, please. like to score metric allow us to detect the fraction, to measure the simulated fraction of true novelties that are the one that are not, that not fall in the usual likelihood score distribution that is in blue. Next, please. And then we were able to emphasize the quality of detections and the ability to distinguish between structure as a Sagittarius trail, moving it deeper in space or in denser environment. Next, please. And then we aggregate all the metrics results in this bar plot that are this figure of merit that allow us to highlight the best performing strategy. Next, please. Then we were able to analyze the distribution of the time gap between observation in the same filter on different filters and compare them to the ideal uniform distribution through decayal divergence parameters. Next, please. And finally, we used those evaluation to analyze the best performing strategy. So the one strategy that give us the most useful time gap, or better saying, the time gap distribution that is more close to the ideal one. Thank you.
Thank you to all of our speakers. And now we have some time for questions. I think we're handing over at 11, or supposed to finish our session at 11:45 now with the shift. So we have about 15 minutes for questions.
Yeah, so please do type them into either the Slack channel or the Zoom chat audience. While you do that, I had a question for Humna. So this proposal that you're making, it does actually leave a fair amount of time for the galactic plane to be surveyed, right? You're making time for that. I wondered if you'd had any feedback from people in the STARS, Milky Way and Local Volume collaboration about whether that was enough time, like how well it matched up with their own desires for the overall LSST survey strategy.
So we did this in the white paper call. So the Olsen et al. Paper that I've linked on the previous slide was like a culmination of work from different collaborations. It was Milky Way, Solar System, and desk representatives, I guess. And then the idea is that because you can actually optimize the cadence itself, you are actually getting more visits to specific regions of the sky that weren't really getting those visits anymore. So far, I haven't gotten any, I personally don't know of any negative feedback. I don't really know of the metrics that well to kind of just play around with it. And I'm hoping that at least tomorrow's session is going to be a good place to kind of get a sense of what people are thinking and like how we can kind of push for this and then figure out what tensions there are.
Can I make a comment? I don't know how many questions are in the queue, but I would just wanted to say, oh, great. I'll chat. So we did a bunch of simulations varying the survey footprint, and we'll talk about this. Well, it's in the pre-recorded content for tomorrow, so we won't actually talk about it during the session, but it's in the pre-recorded content. And from my point of view, determining the survey footprint is the next sort of big thing we need to understand for the survey strategy, because it does influence a lot about like how you can cover the galactic plane and the galactic bulge and the northern ecliptic spur, things like the Magellanic Clouds. And from what I see from the metrics that we have, which admittedly, there are lots of areas of missing metrics, but this kind of footprint seems to do better. This kind of footprint, when you add in coverage in the galactic plane and the northern ecliptic spur and the south celestial pole, when you add those other areas in, it seems to do better on a lot of the metrics than if you stick with our sort of classic, more traditional baseline survey footprint. So I think that there's definitely lots of space still to be investigated, but it seems like a fairly good trade. Now, I will say, One of the things in the baseline survey is that we actually were spending more time in the wide, fast, deep, so the number of visits per field was higher. When we go to this new footprint and then we add in the other, the coverage in the other regions, we do decrease the number of visits per pointing in the wide, fast, deep. So that is sort of the trade that happens. It's still not below the minimum, so that 825 visits per pointing is still being met.
So 2 comments, sorry. One thing, so you mentioned that the metrics do better with this kind of footprint. Is it because, so my understanding is that when you include galactic plane or a big chunk of galactic plane in the WFD, you're basically forcing the WFD cadence on that. And the galactic science, is that, I mean, what do you think is the reason for the fact that the metrics are doing better? Is it that they have their own optimized cadence, or is there something else?
So it's not really that because they get their own optimized cadence, it's because they get more visits. In the baseline survey footprint, the coverage of the galactic plane, the galactic center, is fairly low. And so just giving that region, especially through the plane, or through the bulge, more coverage tends to increase the numbers of things like fast microlensing events that you detect. So there are definitely lots of metrics that are missing. I will acknowledge that. And when you decrease the number of visits in the wide, fast, deep, the big wide, fast, deep footprint, you are giving yourself sort of less margin on those metrics. So things like the proper motion all over the sky do slightly worse, but that metric is not super sensitive. So the number of visits is kind of it's kind of pretty slow. So I think that this is understanding the survey footprint is the next big thing that the Survey Cadence Optimization Committee, the SCOC or the SCOC, probably will be looking at. I think they make their own decisions, but I think that the survey footprint is a big lever that we need to look at.
And then regarding the fact that you lose a number of visits, there were some ideas about perhaps we can change the exposure time. So right now it's 30-second exposure, but what happens if you change it to 20-second or 15-second? Or, I mean, you effectively increase the number of visits. How does that impact other science? I know, for instance, weak lensing really only cares about how many times you go and take a look at the patch of the sky. So they actually would be okay with those kinds of visits, at least in theory. We don't have a simulation for that, but do you think that's something that's still can be pursued?
So I know that decreasing the visit time does decrease the individual visit depth. And that is maybe sort of problematic for some science. We do have a simulation in the current set of experiments where we varied the exposure times so that we got to about constant limiting magnitude per visit. It's not a big change. And in that particular version, because the mean visit time increased slightly from 30 seconds to 32.2 seconds, you actually got less visits overall. Same on sky time, but slightly less visits overall. So that's obviously something you could go back and reconfigure slightly. It's a little bit problematic to plan to go to shorter visits in all bands because U band is already read noise limited instead of sky noise limited most of the time. And G band starts to get into that regime a bit too. So in those bands, I would actually consider making those exposures slightly longer. But then because U-band is so critical for transient classification, you still need to keep up the number of visits. And so then we're talking about do we shift the visits from redder filters into bluer filters slightly or not? And there's tension there between galaxies and solar system and transients and supernova. So these are all great questions.
Yeah, thank you. I think we have time for just one more, and it was a question left on Slack by Hiranya Peris, who's actually moved on to another session, but I think it's a good one. So Fabio, you've done a ton of work, I think, with the metric analysis, combining all these different metrics. And, you know, as you can tell from the previous few minutes discussion, there's a lot of simulations out there to be analyzed. So Hirani wanted to know, how easy has it been for you to use the existing survey simulations? And is there something that could be done to help improve the usefulness or the accessibility of those simulations? Fabio.
Yeah, sure. It was not so difficult to access the data, simulated data, but the masked array was not so easy to implement it, to access the data itself. So I needed to spend a little of my time trying to figure out how to actually access the data, but it was just straightforward once I had the line from Peter Joachim, and so maybe this could be helpful, making the accessibility more easily and intuitively for others that maybe cannot rapidly ask to Peter how I can access the data.
Yeah, it sounds like a little bit of direct contact with Peter or Lynne or someone seems to go a long way. Yes,
because there are all the masked. I don't know what is the proper term for the kind of object they use it, but actually the data were basically masked at first place, so you have to reveal the metric values from the opsims. So maybe that was not so intuitive at first. Once you can ask to someone how it worked, it became easy to find a way to access the values themselves. But that was for me. I'm talking from my experience.
So for clarity for other people, I think what you're talking about is not the simulation output exactly directly, but the metric output from math.
Yes, exactly. Yeah.
And these are things. This is something we've noticed. Like, we have tutorials about a lot of this material online. And there is, in one of these tutorials, there's exactly that line that you're talking about. How do I read back in a metric output and access the data and then do other things with it? But we've had the problem of discovery for these tutorials. And that's a great question. We're open to suggestions on how we can make that easier.
I've certainly noticed that community.lsst.org now has a lot of useful information about survey strategy and simulations. I think, Lynne, you are one of the most prolific posters on there. So that's certainly where I would encourage people to go look, whether or not they're in a science collaboration. Is that fair?
I will also encourage people to go look at community.lsst.org. In the survey strategy section is a great place to discuss the survey strategy and various options. And we're trying to also post stuff there as well as in various reports. It gets it into a public place that anybody can see and comment on.
Definitely. Well, we've managed to give you a full 30 minutes of high value here. So I think, Lynne, do you want to wrap it up? I think there's a few more comments going in the Slack channel that will stay open for the rest of the meeting. So that's the place where you can continue to ask questions of the speakers. Lynne, is there anything more to say before we?
I just want to thank all of our speakers again. You guys were fantastic, kept perfectly on time, and had really fabulous content. Thank you.
Thank you for sharing.
Thank you for sharing.
Thanks, everyone. Enjoy the rest of the day.